Welcome to Sander Greenland. Thank you very much for agreeing to give this talk. This is a talk arranged on behalf of the medical section of the Royal Statistical Society. If you want to know anything about bias in epidemiology studies, Sander is the person to go to. Google bias, and there are many, many papers or book chapters or books written by Sander on the topic of bias. But previously, well, I looked to him to misclassification bias, but now Sander's turning his attention more to our biases among statisticians. So the title today is Metastatistics, Seeking Treatment for the Philosophical and Psychosocial Diseases of Statistical Science. Very thought-provoking title. Just before we start, can you please submit questions to the chat? And then I'll either read them out or you can ask them at the end. And there might be a possibility of also putting your hand up at the end, but submit any questions to the chat. Well, welcome, Sander, and thank you very much for coming.
Thank you for inviting me, having me, and putting up with this talk. I can't see you and you can't see me. That is everyone in the audience. So this is going to be just a review or overview of a collection of slides that I've accumulated over the years, varying them in talks. And since my time is limited, I really can't cover much in detail. So the point of this would just to have a flavor of the kind of topics that I've been covering. And you'll be able to refer to the article cited and to the slide set, today's slide set with some corrections as noted, after this talk, so that these slides are going to be posted. But in case you want to hear my overall commentary here and some reads of the slides, you mentioned that the title was provocative, perhaps. These titles that I've chosen over the years have expanded as the titles in general, I've noticed on papers and such, have been expanding to abstract length. But here are some past titles. Well, let's see, I'm not getting page down. No. Let's see if I can get down here. Having a little technical there. So here's last year's slide title, toward restoring realism in statistical training and practice. This is about preparing for the harsh realities of a scientific world, and I emphasize the quotes, in which statistical inference, in quotes, is often a device to manufacture desired conclusions. Or to use a quote that apparently dates back to the mid-19th century at least, there are lies, damn lies, in statistics. This was apparently used by one of the presidents of the Royal Statistical Society at the end of the 19th century, but it had already been circulating. Here's some earlier overlapping talk titles. Advancing Statistics Reform, How to Improve Statistical Science in the Face of Resistance. There has been some concerted resistance to the kind of reforms that my colleagues and I have been pushing for. Then cognition and causation before probability and inference. This is one of the problems that we talk about, is how probability has been used as a foundation for statistics for a couple of hundred years, but especially in the 20th century, the time I was coming up, it was considered the whole foundation. And we come to realize that was also undermining statistics understanding and application. If we're talking about applied statistics and not just statistical mathematics, some branch of math that's called mathematical statistics, then we're talking about inference, and that in the real world involves cognition, and it involves people seeking causes and also having to face what causes their data. So another title was Breaking the Tyranny of Statistical Authority Over Rational Cognition. See examples of that soon. And then there's my favorite title, which if I ever did write all this up, it might be my main title. There's not much science in science. It's I'm in that camp, which we could go back to observations from people like Thomas Kuhn, for example, who was an influence on me when I was young, that that the science is the social process that has gotten uh, turned into essentially some kind of scientific religion that, at least in large quarters, and it seems to have gone by what was its idealized mission going back to the 19th century when the term scientist was coined, that the idea that we're just pursuing what really is, whatever it is, regardless of the consequences. Now everybody frets over the consequences of what they might find, and therefore spins their everything from the design to the collection of data to the analysis to the interpretation and then the publicity, spin it in the directions that whatever it might be that they are preferring. So we'll talk about that in some of the slides here later. The key observations about is that statistical analyses are based on vastly oversimplified models that omit major sources of uncertainty and that ignore most bias in data generation. And that includes the personal and social biases. They encourage overconfident inferences and conclusions because of that. And statistics primers, the elementary coverage, and study reports display overt misinterpretations of these unrealistic statistical analyses. And then the advanced statistics treatises are mostly just doing math, which, and then the numbers in there that may be taken from real studies, they're mostly just numerical illustrations that don't begin to approach the complexity of the topic that they're being applied to. And all these misinterpretations are amplified in reviews and popular science communication. When the primary authors have stakes on the conclusions, motivated reasoning strongly determines the direction of misinterpretation. Favorable errors get overlooked or they're denied. Unfavorable errors are vigorously sought out and eliminated. So there's this selective analysis of both their own study and the literature, where I've seen this consistently, where everybody that I know knows that you can read any paper and find things that we would think are mistakes. Sometimes they're very minor, sometimes you find the paper excellent and the errors seem to be small, but sometimes the errors are large and they've been overlooked or glossed over or denied even. But what we notice is that the errors that get glossed over are the ones that would militate against what the authors are trying to conclude. And the errors that get rooted out and accounted for as carefully as they can are the ones that, where doing so would favor what the authors want to conclude. There could be no surprise to anyone knowing human nature and that scientists are human. What was interesting is that to find many lay people treat or think of scientists and scientists, the journalists even have sometimes presented scientists as a priestly caste that is somehow morally, ethically superior to the average person. This is, of course, much the same as clerics in religions are treated. In fact, to me, the parallels between science and organized religion, science with the big quotes, with the capital S as practice, are just too astounding to be overlooked. And they're completely unsurprising in light of the fact that we have the same people with the same kind of genetic background and endowment running these institutions, running these things. Now, this, of course, completely rankles most of our colleagues, we should have no surprise if you're attacking a church. You can, olden times you would get burned in the stake or excommunicated. These days it's simply excommunication. But I think that science as a whole has become overdue for the kind of reforms, which, of course, when the church faced reform in the 16th century, that led to horrendous wars and, of course, schism, which is maybe setting up for, but perhaps not. What I want to talk about are the cognitive biases that contribute to all this. They're ritualized and institutionalized by statistical training, then are used to produce or support false claims or inferences. So we need to learn to admit and teach about investigator and cognitive biases. We need to do this if you claim to be opposed to what I describe, and you accept the notion that, I will attempt to illustrate, that this is a major problem in the literature, the human element, then you would need to teach about investigator biases, human biases, cognitive biases that affect people naturally. They're inescapable. They're just like, as has been said, optical illusions that you can't escape. It's the way our nervous systems are set up and our social systems are set up in consequence. And we have to cover those and account for those just as we do with mechanical, physical biases like confounding selection biases and mismeasurement biases from measurement failures and misclassification. I've devoted most of my career, most of my published articles on methodology to dealing with the latter mechanical biases, but in latter years I saw that it was only addressing part of the problem. It's as if one's only dealing with the problems, with skeletal problems in the whole health of the individual. And here we have a system, science, where it has this admirable skeletal structure, but the patient is sickened by psychological afflictions. The title at one time, point that I used, I didn't list here, I talked about, was Statistics as the Sick Man of Science. There are some of us who view it that way, although it is really all sciences suffer from it, but statistics, being, as has been said, the servant of all sciences, has transmitted these problems along and aggravated them. These biases are large, pervasive, and important to society, and yet they're overlooked by most methodologic texts and literature. Show me statistics books or epidemiology, my specialty area books, that discuss these at any length. I haven't seen them yet. There's some brief mention in textbook that I was a co-author on, Modern Epidemiology. But you can also note that my view is shaped heavily by the area in which I've been in application, that's in health and medical sciences. And the social forces, the financial forces, the political forces, the ideological forces there are so strong, they easily overwhelm all the methodologic fine points that I've devoted far too many papers to discussing, and which are the central point of emphasis in most textbooks I see. And I argue that in basic teaching and applied statistics, the coverage of these kinds of cognitive issues should displace many fine points of statistical methodology. I don't see where working scientists using statistics need to know in any detail about maximum likelihood and how that's somehow optimal under some very artificial conditions or anything like that. The idea that material, which I used to teach and think it was important, that should displace coverage of these far more important forces. It's just absurd, and it's destructive. And then statistical methodology is itself a major contributor to cognitive biases, especially the ones I've labeled nullism, dichotomania, and overconfidence. One form of nullism, to talk of that, is the bias of assuming all incentives are to discover rather than to refute effects. And this is a meta-bias. It's rampant in the replication crisis literature, which ignores differences in incentives across topics and authors. And for example, what you'll see, what I see in the replication crisis literature is just endless going on and on about false discovery, false positives. How do we fight false positives, false reporting? Well, those are a real problem, but anybody in screening for a disease knows that false negatives are a serious problem too. And anybody who reads and understands any scientific literature knows that false negatives can be a major issue, a very costly one socially, if we miss useful treatments because we got a false negative on that, if we miss dangerous side effects because we got false negatives, those are serious, costly harms. But those invested in a treatment are biased towards reporting no excess of the adverse side effects. And I'll give an example, I believe an example of that below, if I get to it in time. And there are many other settings in which statistical norms will aggravate null bias. So if we look at investigator bias and the motivated reasoning we get from that, the social pressure, those are candidate explanations for conclusions in abstracts, reports, and articles. When you look at an abstract, I look at an abstract of conclusions of an article, the discussion, I've come to realize it's just as important as to look at what motivations might be there, to present things the way they did, choose their words the way they did, their presentation. That's just as important as looking for the confounding, the selection bias, and always the measurement error that they didn't control for. And publicized results are a mix of targeted effects and biases, all the biases. Hence, they're never fully unbiased or reliable. But they get presented that way, some of them. Reasoning motivated by personal, legal, and financial stakes fuels resistance to serious reform of statistical training and reporting. This is my opinion. I've seen this all over. There's a whole basically industry-supported viewpoint that will cling to these standard ways of doing things because they have the most to lose from change. That's no surprise. Again, it strikes me as incredibly naive to think it would be otherwise. Again, we're dealing with a human process. Here's an example of a blatant one of political bias, of the sort that I was just describing. A special interest lobby forced a statement of fact to be followed by a false claim, in red below. So what I noticed long ago, decades ago, that U.S. dairy products in the United States, if they had this label to tell the consumer, and just a statement of hopeful fact, and hopefully they're telling the truth, that the milk was from cows not treated with recombinant bovine hormone, this was a statement. They are forced, still required to add this disclaimer as an asterisk below it. No significant difference has been shown between milk derived from cows treated with RBST and those not treated with RBST. Now, you should ask yourself, first of all, what the average consumer, 99.9% of them, what would they make of this statement? They certainly wouldn't make of it with that something like, oh, P was greater than 0.05 in some study or studies or something. They would look at this and just say that they've been forced to state that this doesn't make any difference at all for anything. So this is a grotesque statement in and of itself, especially to put on a public label as opposed to some article for scientists who at least might have enough statistical savvy to understand what they might mean by significance. But let's look at the actual data that came in, that was around at the time this got lobbied into existence. There were 8 trials, experiments. 19% average increase is what they found in somatic cell count, which is pus in milk from cows treated with RBST. So there was this elevated level of pus. But if you look at this graph, you'll see that most of the studies, and this is how it was done, most of the studies were said to find nothing. They found no increase. Why? Because P was greater than 0.05 in those studies. So you could contemplate this graph and understand how it was told to the regulators and the congressmen, the people who they lobbied with to get this kind of labeling, that most of the studies found nothing. And there's bound to be a few flukes. Of course, that would overlook the fact that most of the studies saw association in the same direction. A couple had p greater than 0.05, which is more than you'd expect out of mere 8 studies by chance alone. And that the summary, if you did actually a summary estimate, you'd see that it had p much less than 0.05. But all those sophisticated elements weren't in play. So first lesson, reporting ambiguous statistical results as negative or no association generates spurious claims of conflict or refutation, even when the studies agree. And this happens a lot when the initial studies get p less than 0.05, and later, often smaller studies, as clinical trials tend to be due to their expense, they get p greater than 0.05. So a common theme is that we get observational studies that got p less than 0.05. They announce they found something, an association, hopefully not an effect. And then clinical trials are done and they refute them because they get p greater than 0.05. And the big focus is on this so-called conflict, not doing a direct comparison of the results, not noting that the trials are smaller and are bound to have lower power and get p greater than 0.05 for the same size association or effect, not noting that the populations are very different, that the observational studies are these free-living populations, and the clinical trials are carefully screened to remove people at high risk because they would form a liability in conducting the trial if there was harmful effect, and they're done under very controlled practice conditions. So the result, we get headline-grabbing false claims from invalid use of null hypothesis significance testing, such as claims that most results fail to replicate, something that I have never found correct in any topic that I've looked at in health and medicine, where you did a careful analysis of the original studies and the so-called replication failures. You put them all together. What I found was always shockingly, as in the previous example here, where some might say there was conflict because most studies got p greater than 0.05 and some got less than 0.05. If you did a careful analysis, you'd find that, first of all, the heterogeneity had p much greater than 0.05, and the overall effect was very similar in statistical terms. So we also get these claims that most observational studies get refuted. Again, I haven't got a real example where this really bore out under careful analysis, especially when one took account of the large differences often in the populations that were being examined, the conditions being examined, and even the treatments being examined and the definition of treatments, the different definitions of how many prescriptions they were getting and the rate at which they were getting dosed and so forth. Here's an interesting example of a claiming refutation in the face of perfect agreement. So here's something where instead of claiming that there was some kind of refutation due to differences in p-value, this is equivalent to that. There was an article that claimed the use of statins was not associated with risk of glioma. Now, if you want a little background, statins affect cholesterol metabolism. That's supposed to be one of the major points of action, and people always worry about what's that going to do to the brain, because after all, the brain has his organ with the most cholesterol in the body, very dependent on cholesterol metabolism. So what do they got? What do they get here? Odds ratio of 0.75 for an arbitrary cut of greater than 90 prescriptions. They didn't explain where that was from. Look at the confidence limits there, what I call compatibility limits. You can see that they cover this huge range, mostly on the lower side, but some on the higher side. So they conclude our findings do not support previous sparse evidence of a possible inverse association. They claim then and end with, our study revealed a null association between statin use and risk of glioma.
Now, when I present examples like this, I always, when I used to present them in a live audience, there would always be some statisticians who say, well, you're just going on about people who don't know what they're doing or talking about statistics. And I said, I see this every day I open a medical journal, a health journal, every day, everything that comes into my inbox. This is who is responsible for this kind of work if we're not? Here's the reality of this context of what they're making their claims. Their results agreed perfectly with previous studies, which reported these odds ratios, 0.72 and 0.76 versus their 0.75. And they're confident, their interval estimates were narrower, meaning they were less sparse, they had a larger effective sample size than that study. When you did a summary odds ratio across these three studies, you got 0.75, and now you got p equals 0.0016. So what you could see in this little literature is that there is indeed an inverse association across the studies, regardless of whether that reflects prevention by statin use, which is possible, bias, or some combination of the two. It's utter misinterpretation to achieve some kind of a claim that they have discovered something, they've revealed something new. And you could call this novelty bias, if you want. Now, here's an example of what I would call motivated bias, upward p-selection. Or null hacking. All the time when I see talking about p-hacking in the literature, which is a problem, it's about people supposedly hacking to get p less than 0.05, figuring out some way, maybe fiddling around the covariates in their adjustment, whatever it might be. They've got to get p less than 0.05. What they don't notice, they never seem to notice, the cases that I notice, like this one, where it appears, even just from what they're presenting in the paper, and who knows what goes on elsewhere behind the scenes, or it looks like they're hacking around to get an analysis to get p over 0.05. The Cox model adjusted hazard ratio, which is the usual standard had been for reporting here, got a hazard ratio here of 1.6 with these 95% limits of about 1.2 to 2.2. So they switched to a thing called high dimensional propensity score adjustment, which in the form that they were using it, this is technical detail that not everyone would hip to. The particular form they were using it was particularly inefficient, which means it would tend to use standard errors that were a little bit too large. They got 1.6 again, but now the 95% limits expanded to, and this is what they reported, not 1.00 like they had everywhere else, but now they're reporting 0.9997 to 2.59. So they go out, they're now doing a 3-digit past the decimal point reporting to make sure you see that one is inside the interval. They did mention in passing in the paper that they had an earlier meta-analysis paper that got a hazard ratio of 1.7, basically practically the same as what they saw here, with an interval from 1.1 to 2.6. What they didn't mention is that there were also further studies since then with similar results, just like this, that their p-value for the hazard ratio of 1 was 0.505, which is that what that would tell us is that all hazard ratios from 1.01 to 2.58 had p-values larger than 0.051. In other words, they had p-values larger than the one for the null. And they would also have a likelihood ratios relative to the maximum that were bigger than the null, one for the null. So instead of noting all this, basically that these studies, regardless of whether this is caused by confounding or whatever, these studies are consistently coming up with this association. But instead, the press concluded, in the paper concluded, and this is a quote from the paper, in utero exposure was not associated with autism spectrum disorder. Not associated. This is a lie. This is a flat out lie in the face of the data. Not that I'm saying they are liars and they knew they were doing it, but to look at these data to look at these results and claim that there was no association is a flat out misrepresentation of what the data actually provide, the statistics themselves, through the statistics themselves. There is an association. Whether it's causal or not then has to be debated, because after all, this is not a randomized study, and there are further ways of analyzing it to try and control the confounding better, which at least expand the confidence limits, I call them compatibility limits, and which provide a different perspective on it. This is an example. And the fact is that articles decrying null misinterpretation of non-significance date at least back to Pearson in 1906, where he said, absence of significance relative to the size of the samples is too often interpreted by the casual reader as a denial of all differentiation, and this may be disastrous. So he said himself this in 1906. So this is almost 120 years ago. He must have written this 120 years ago. That to say, if we translate it into modern terms, getting a large p-value, and he, by the way, used the term value of p, that's how far back that term goes, is not to be interpreted as a denial that there is some kind of difference. And this kind of misinterpretation could have a severe effect. Others repeated this caution since, including R.A. Fisher. So why then does misreporting of ambiguous results as null, this nullistic bias, continue and it's even enforced by some medical journals? For decades, medical journals have required people to state there were no association or no significant association because p was greater than 0.05. To basically misstate results like this in this fashion. And I'm not saying these authors, the authors are lying. I think they would probably believe this. They actually thought that p greater than 0.05, which they barely got by a 1% of 0.505, they actually thought that magically translates into no association. Well, it does in some minds, in many minds, and many readers' minds that have been warped by statistical methodology as taught and practiced. And the problem here is human factors. Statistical practice is plagued by researcher biases such as dichotomania. So even when a continuous picture is needed, and I say it's needed almost all the time, as in these examples, the practical limitations force us to present dichotomizations such as compatibility intervals, interval estimates, which are mistaken for truth indicators or behavioral directives. And this curse of behavioral directives, we can trace that directly and explicitly to Neyman and his behavioristic statistics, which was so mechanical and so done in ignorance of the human factors and goals and so forth, that even Egon Pearson, his partner in inventing that system, backed off from it in the 1950s and pointed out that he did not follow Neyman in this fashion. And then we have nullism, that even when there's insufficient evidence to reject even an effect direction, we will misinterpret ambiguous evidence as supporting no association or no effect. There's this chronic problem. You can do, you could say now, with the standards being what they are, you could do a study of size 1. So you'll have confidence limits, or you could have limits going from minus infinity to plus infinity if it's on that scale, or 0 to infinity on a relative scale. And you can now say your study showed no association. It's evidence for no association because you included the null value in your interval. So here's an example of how the press picks this up. We get incompetent press reporting even when the original study reports are a tad bit more careful. There was a randomized trial recently published last year of vitamin D, 2,000 units a day, and upper respiratory infection. And the abstract said they got a non-significant result. And the odds ratio here was 0.6, with that interval from about 0.3 to 1.3 among the people who had a low baseline vitamin D, serum vitamin D level. Now, what does this translate to? We're constantly using two-sided intervals, but the whole point at issue here is whether this help prevent upper respiratory infection. I don't think there's a lot of credibility that it would aggravate it, cause it, or anything like that. Here for one-sided p-value is about 0.1, a little less than 0.1 for having an odds ratio greater than 1. So if we flip that around, if we did a reference Bayes posterior odds on this, it would be that we'd get an odds that exceed 9-1 that there is a preventive association here or effect, given that this was a trial. So that we at least could say that this was not at all definitive, but it's certainly pointing in that direction of prevention, and so more research is needed. But what did the medical newsletters and the consumer newsletters report? What was their headlines? Well, here's an example of one. Supplements did not reduce the risk in those who were vitamin D deficient at baseline. That is a false statement. It's just completely false. We can't say that. We'd say actually the correct thing would be to say, even though the results aren't definitive, they favor an effect among the deficient. And we should not make the mistake of passing up, pinning down more carefully what the effect is. This is promising. This is a cheap preventive that's available everywhere, and people are taking it for other things. So it would be great to find out that indeed, if this was panned out. But here they are essentially putting a stop to that kind of progress. So most of what I see reported in the study found no association is instead misreporting of ambiguous results, often pointing in a clear direction. This kind of distortion could be mitigated by requiring students, when you're training them, to drill them in doing this, and then requiring research reports to tabulate or graph p-values across a range of parameter values, the effect sizes or whatever. For example, if the issue is whether there's some kind of causal effect, you would give p-values for hazard ratios of 1. That's the standard null p-value, and the only one that gets presented in almost all reports. But you'd also give the p-value for a 50% increase and a 100% increase, and maybe a 200% increase, or at least a whole set of possible values that were considered in candidates before you did the study, including whatever value was used to calculate the study power, if that was a design factor. And if you were looking at a preventive case like the one we just saw, you would give p-values for 1. Again, the null case, but also for 2/3, for 1/2, for 1/3. And in fact, in the previous example, this one, we would see that the p-value for 2/3 would be very close to 1. So that this was as we'd expect, because the MLE is at 0.6, 2/3 is 0.67. There are these incredibly simple things that can be done to mitigate, or at least try and push people away from this kind of error. Of course, this may be fighting against human nature, but that would be a good use of statistics as opposed to going along with human nature, declaring results to have shown this or that. So, and it's so simple to do. When you do, as they did in these studies, a regression like a Cox regression, you get an estimate of the treatment coefficient. The coefficient is beta, the estimate's B in this slide. And the p-values that are being presented are usually just computed from the z-score, the Wald statistic that is the difference between the MLE and the hypothesized value, which might be 0 for a log odds ratio, over the standard error from the program. So all you have to do to compute p-values for alternative values is just compute their z-values, plugging in different values for beta. And there, of course, you'd find that the 95% compatibility limits for beta have p are the ones where you get p equals 0.05 from a two-sided p. And you'll see that many, if not most of the beta in the interval will have a higher p-value than does the null hypothesis. So that you'll hopefully see from that concluding the study supported the null. Other mistakes like that are absolutely unsupportable if you do the statistics correctly. This is not changing any formula. fundamental formula. It's just using it more flexibly. Now, this is the huge problem I've seen coming up. It's embarrassing for me because for 20 years, I did workshops all over the world in Bayesian methods. And for what I found since then, as Bayesian methods appeared more and more, informative Bayesian methods can worsen overconfidence and null bias by narrowing and shifting interval estimates. And as with significance testing and multiple comparisons adjustment, I distrust Bayesian reports in the medical literature. When I see these, it's like I know I'm almost certainly going to be in for trouble if they're using informative Bayes opposed to reference Bayes, true reference Bayes, not uninformative Bayes. That's another problem that I won't have time to go into. Their priors typically have unjustified overloading towards the null. This is the one major problem. And then they misreport their overshrunk and overprecise posterior results as if they were results driven by the study data. So let's go for an example. This is a randomized trial of ivermectin and COVID outcomes. So this is a red hot topic, and the social pressures here in the major journals like this one are all to find nothing. It's like it was all to refute ivermectin and also, of course, hydroxychloroquine. There's a similar story there, but I'll just do this ivermectin example. It reports posterior results without giving the prior anywhere in the text of the paper. I could not find what this prior distribution was that they were using to produce these results. They did say that they had a pre-specified minimum meaningful difference, that is a hazard ratio of 1.2 for, and this is a higher value above 1 is a benefit. That is the on hazard for end of symptoms. They say corresponds to a 1.5 day reduction in self-reported recovery time. So here's the posterior they report for the hazard ratio, 1.15 with 95% limits, 1.07 to 1.23. The posterior probability, if I back calculate, and you can back calculate from those results, the posterior probability, they don't say this give this in the abstract, it is buried somewhere in the text, the posterior probability of the hazard ratio being greater than 1, that is, there being a benefit, exceeds the superiority threshold of 0.99. In other words, if you look at those limits and you understand how these things go, you would not be surprised to find out that the posterior probability of a benefit, of some benefit, no matter how small, is over 99%. But that's not what's played up. Okay, they report on another outcome, COVID-19 related hospitalizations and deaths. These are just related, which is generally was there a diagnosis at the time, not necessarily that they were caused by. These aren't adjudicated that I know of, that I could see. No, and that was certainly no association right there. But the posterior probability that the hazard ratio is greater than 1.2, again, back calculated from what they presented, was about 20%, 1.192. And the median recovery time difference was over 2 days, just actually about 2 days, with 95% posterior limits of 1 to 3. So they state ivermectin for COVID-19 is unlikely to provide clinically meaningful improvement in recovery. That's their conclusion. Nowhere in the main text do they give the prior use to get that conclusion. Nowhere I could find. And nor did they give the frequentist results for comparison. This is remarkable because you can see from these posterior results alone, whatever they mean by unlikely is that they mean 19%, if you want. That's unlikely, and they're going to dismiss it out of hand, given that it's, again, all in the direction of benefit. Well, the numbers, here's the best I could do with what I saw in the published article. I could back calculate the 95% confidence limits, that is what I call compatibility limits, from the MLE. That the MLE must have been somewhere around 1.8 close to 1.2, with limits of around this 1.12 to 1.26, with p equal to 0.41 for the hazard ratio greater than 1.2. And that would mean that a Jeffreys prior, this is one of those reference priors, would produce a posterior probability of a clinical meaningful benefit, that is a hazard ratio greater than 1.2, of over 40%. And what would it take to shrink down to their results from those results? Well, my back calculation was that it would take a mean zero normal prior that was centered at 1, for on hazard ratio scale, and had 95% prior limits from 0.89 to 1.13. And that gives a prior probability of a hazard ratio of 1.2 of 0.1%. In other words, their prior was 99.9% sure, over 99% sure there was no clinically meaningful benefit. This result that they're presenting is strongly loaded against finding a clinical meaningful improvement. It is basically deriving the result. It is not that the data shows that there's any kind of strong or even probable evidence against there being this clinically meaningful benefit. It's that their prior drove them into that conclusion.
5 minutes, Sander.
Yeah, okay. I did other calculations with other priors. The point is that the strong priors were not justified by previous trials. If you actually look closely at, and there's 50, 60, I don't know how many now, trials, some of them are fake, some of them are horrible, some of them are fine. They don't justify priors this strong. And even if they did, the result that they're presenting is not telling you what their study found, their trial. So, to bring up here, my message here is that we should require Bayesian results. Every time you see a Bayesian result, it should be preceded by and accompanied by, at least, by reference results from the same sampling model without the prior, which could be tabulations either of the frequentist estimates and p-values or the posterior estimates and tail probabilities from reference priors like Jeffreys priors or maximum entropy priors, which in our field are very close to frequentist estimates and to p-values. Okay, those reveal how much the posterior was driven by the prior rather than the actual study data information. They should also be forced to present their prior distribution in detail. And the typical priors that I see represent opinions whose certainty far exceeds anything derivable from actual data, like a fair meta-analysis. I say this stems in part from biases being reinforced by social feedback loops. And these loops form an echo chamber effect, exaggerating content of authoritative opinions far beyond anything traceable to the actual data. Where did they get such a strong prior and use it without reference to what they were presented? So what would it take under a proportional hazards model? A perfectly balanced randomized trial with an estimated hazard ratio of 1 and about over 1,000 observed events to get an interval estimate that narrow, around a hazard ratio of 1. What you should do to check a prior is see what kind of study would produce its 95% limits. What data, what perfect randomized trial it would take to produce the 95% prior limits as the confidence limits from that trial. And the answer in this case, it would take a perfect trial with over 1,000 cases, 1,000 observed events to get an interval estimate as narrow as the prior limits that they were using, of the prior that they were using. So this is how extreme bias can be. And something I've got to say before, so Bayesian hypothesis tests that people have been pushing to replace null hypothesis significance testing, the standard form, have been pushed. They use a prior mass of 1/2 for a point null, and they're an even worse deception. By any sensible measure, the information in a 0.5 prior mass is far beyond what can be justified by medical literature. That mass translates to data with a likelihood function from an infinitely large experiment, one that has a point mass, produces a point mass as its posterior on the null. That empirical absurdity is then given a massive 50% weight on the posterior. So what I've seen is that Bayesian methods have been promoted as some kind of cure or suitable replacement for the traditional methods, the conventional methods that remained the standard. And what I've seen is that people have figured out how to abuse them and institutionalize these abuses in ways that are even worse than what I see, or just as bad, and what I see is even worse than with the frequentist methods. This is very disheartening to me, as I said, as somebody who conducted workshops all over the world about how to use Bayesian methods, how to use them correctly, and so forth. Clearly, there's a human element here which just simply giving a line by line correct training cannot overcome. It has to incorporate the human elements here that are going to move towards and take hold of and even institutionalize distortive methodology that is easily manipulated to produce the results that the researcher or their whole research group, social matrix, their funders, whatever, what people want to see. This is, to me, the largest problem today in science, medical and health science, certainly, and statistics. Okay, now I must be out of time, right?
Oh, thank you very much. I think I've disappeared. I can't see myself, but we've had a couple of questions in the chat. I don't know how to see the hands raised. Janina, I don't know if I can see hands raised, but we've got a couple of questions, but maybe I could just ask one. Oh, somebody's clapping. Oh. I just wanted to ask one rather basic one, but just my own sort of bugbear, really. Do you think, well, it's a rhetorical question, I have to say, we statisticians are biased because before you even do any modeling, we're biased to think that the data quality is perfect because statisticians don't seem very interested in data quality, and that seems so fundamental before you do any modeling. So I just wonder well, it's not totally a rhetorical question, what you think about that.
Well, I completely agree. It's if I could go on, I've got through 31 of 140 slides. If I went on, I would have been going on about that at some length. I simply put in the front of this talk the slides that I thought for this group I should get through emphatically. But yes, of course. I mean, what I go on about later, and I've done it all over the place, is how the statistical methods we use, and I mentioned this, but in these slides that I did show, the statistical methods we use assume a perfection of the data, or assume that whatever imperfections have been accounted for by our adjustment methods, which themselves are full of idealizations and assumptions that you really wouldn't believe if you understood the material in detail. And I could go into great depth.
Oh, we have quite a few questions now. We've got a couple from Stephen Sen. I don't know if you'd like to unmute yourself and appear or you'd like me to read it out, Stephen. Are you there, Stephen Sen? Shall I start reading his question out then? And then maybe if you wish to appear.
Can you hear me? If you just read it out for everyone, that would be great. Thank you.
Okay. Kenneth Rothman, 2014, has argued that representativeness is not necessarily relevant to epidemiological studies. Yet in your discussion of the cow's milk data, you claim this as a superior feature compared to experiments. Do you disagree with Rothman on this?
Wait a minute. I think I missed something in the middle there. Can you repeat, please?
Oh, sorry. Kenneth Rothman has argued that representativeness is not necessarily relevant to the epidemiological studies. Yet in your discussion of the cow's milk data, you claimed this is as a superior feature compared to experiments. Do you disagree with Rothman on this?
That's the word I'm missing. What data was that? The Cosmo data?
No, sorry, the cow's milk. Sorry, cow's milk.
Cow's milk data. Oh, right. Exactly. To me, this is one of those things where if Rothman said not necessarily, he's putting a qualifier in there. the answer to most questions like that, as far as I'm concerned, is what's the context? To really come up with an answer, you have to put yourself in the context. And the context for the cow's milk data is one where you have all this political pressure and you have data being presented in a way which is, I would assume Stephen Sen would agree that this isn't a proper way to summarize the data by saying, oh, most of these studies didn't find anything, because most of these studies were little studies that got p greater than 0.05, or in the current way of acknowledging the problem, they were underpowered. So I'm really not sure what that question is getting at, but the answer is I do not completely agree with Rothman. No,
Stephen's there. I don't know if you want to speak, Stephen, because you had another question.
Yeah, can you hear me?
I can hear you.
Me now?
Yeah, I can hear you. Can you hear Sander?
I did, and then I don't. Go ahead.
Carry on. I think we can hear you. Stephen? Oh.
He comes and goes.
Oh,
can
right.
you hear me now? Can you hear me now?
Yes.
Yes.
Yes. Okay. So I agree. Thanks for a great talk, Sander. I agree with you entirely regarding the analysis of the studies, overlooking the meta-analysis, overlooking the trends in the studies and everything. But then you gilded the lily by saying, and some of these particular studies are using cows that are roaming freely, and that's going to be much better than actually using trial data. And that's the point at which I thought, well, you don't need to do that. You don't need to make a claim like that, because the data you have are what they are.
Okay. I don't disagree. I mean, to get into any one of these examples in further detail would require a lot of detail. I just wanted to underscore how these things look. If you just step in one level to look at the kind of data that produce these kinds of statements, or, well, in this case, a mandate on producers all over the United States. It's very strange.
Thanks.
Okay, sure. Oh, should we have another question? Because quite a lot of questions popping up now, and I can't see any hands. So Janina, I don't know if you can. So Simon Day.
There are no hands raised, Marie. Just carry on reading from the chat.
Speak yourself, or would you rather I'll start reading it out, and then Simon, if you want to pop up, you can.
Well, I think can you hear me? It's Simon here.
Yes, I can hear you. Yeah.
Okay, jolly good. Well, it's just a comment, really. I mean, thanks for a great talk, and sad to say, I agree with everything you say, and it's a dreadful situation we're in, isn't it? I don't know what the solution is, but my comment was really about Bayesian approaches, and essentially saying that nobody reading a paper with looking at a conclusion from a posterior distribution should believe it, because everybody is allowed their own personal prior, and so will end up with their own personal posterior. So I can read the author's posterior, that's fine, but I should be interpreting the results based on my prior and therefore my posterior. But of course, people don't do that. They read the conclusions as written and then get on with the rest of their day. So it's just a comment about that, really. But great talk, I enjoyed it.
Yeah,
but you know,
Sorry, I should have said that.
With that paper, that example I presented, and so many of them I see, you can't, they're just putting the Bayesian results up front. That's basically, then you could say, their opinion. My opinion would differ, but I can't even begin to, I have to go through great labor just to even begin to impute what my opinion might be in light of their data, because they're not giving me the key information. This was an old comment against Bayesian methods. Many of them would say the frequentist methods that we use are much closer to data summarization. The Bayesian methods aren't. I think Stephen would say, you know, you give me your posterior, I have to back out your prior and then put in my own. And that's something you can't even do, or can barely do, with these papers.
No, I agree. Thanks very much. Anyway, thank you for your talk.
Oh, yeah, we've got one from Eugene Komarov. I don't know if he's there or would like to speak. I'll start speaking, and then Eugene, if you want to come on. Are you there? No. Keeping the observed beta, lowercase b, constant and varying the parameter uppercase beta in z-score formula seems to be p-hacking. Seems to me this will encourage even more irreplicable results.
That's just a misconception of what's going on. All you're doing is presenting a p-value function, points on a p-value function. It's the opposite of p-hacking. It's preventing, it's actually not doing anything other than showing you how the p-value changes with your hypothesis. That's why you should present them all. And that's why if people are going to rummage around, they need to present all those analyses. And if they can't do it in their main paper, well, these days we have online supplements that can go on indefinitely, and they could all be neatly cataloged as to what people did. Why they're picking out a particular analysis to focus on. If you want to say there's some p-hacking going on, it's p-hacking for the null hypothesis. That's the only p-value that almost all these papers present. You only see this p, and it's only referring to, for example, a hazard ratio of 1. Whereas I want to see what that p-value is for 1.5 or 2/3 or all the other possibilities. And then I will see most of the time that the hazard ratio of 1, the null hypothesis, isn't the most distinguished of these hypotheses. And I will very well will likely see that these data aren't telling me as much as all these conclusions and discussions and medical headlines make out. And of course, that's why it's not popular. That's why nobody's taking this stuff up, even though it's an example of what's needed to deal with all the p-hacking that takes place. There.
Oh, thanks. Over there, sorry. Okay, next question from Gavin Stewart. The one after that's Ria Anna. So if either of you want to pop up, Gavin, if you want to pop up, or otherwise I'll start reading. Do you think pre-registration and robust meta-analysis sort this, or at least expose it appropriately, or do we need something more on the human dimensions, effectively honesty about priors?
Well, it's a compound question. I mean, I'm all for things that would help. I think that it's nice that people, the idea of pre-registration, well, some people do try and argue against it. I don't think it should be required. That would prevent presentation of data that happen to not be pre-registered, things that are not pre-registered. The problems that I've seen is that people, and I'm not an expert in this particular data, but I've seen people say that when they've done studies of pre-registration versus what actually got published, they see massive deviations from what was pre-registered, but it's never reported that way. There's just a statement, this study was pre-registered and blah, blah. And then they go and they actually, if they're able to at all, find the protocol, the full protocol, including an analysis and so forth, and compare it to what was done, they can see that it was what was pre-registered doesn't cover all that was done. And there's a lot of, should we say, unavoidable, innocent reasons for that, just things we all know who've been involved in real studies, how things just can go wrong left and right. People dropping out like crazy from side effects, whatever it might be. We just can't anticipate everything from the start. But we like to think that pre-registration would help. But it would only help if there is some comparison, like perhaps, again, a supplement that says, here's what our pre-registration is, and showing the actual data document, and here's how we had to deviate, this is how we deviate, and why, explaining why. That's the only way I could see that being helpful, and that is a lot of work.
Oh, thank you. Ria, I think you'd like to appear and ask the question, would you? I see you've put a little hand up.
Yeah, can you hear me?
Yes.
Okay, I can maybe also turn on my camera. So, hi. Thank you for the interesting talk. I have kind of two questions that are tied together, so maybe it's okay to ask them both. So one would be, do you think that existing tools like prior predictive checking and prior sensitivity analysis that they alleviate some of these issues that you discussed for Bayesian approaches? And then tied to that, would you say that the discussed issues with specifically the Bayesian results are due to the methods themselves, or rather due to issues in implementation?
I think it's either or. I think all these things are going on. I'm all for sensitivity analyses of all sorts of things, including Bayesian priors. The 0 point, the reference point, the origin for a Bayesian sensitivity analysis would be the frequentist analysis or the corresponding reference, like Jeffreys or Maxent prior type of analysis. That's the reference point. That would be the starting point of sensitivity analysis to see, and then also presenting the priors that goes with each posterior, so that we see exactly to what extent the posterior is composed of the likelihood, and what extent it's composed of the prior. So I don't know if that answers the question, but that's an answer that I have.
Yeah, I think it answers the question. Maybe just a comment that I think when you were saying that, for example, posterior, we should not believe. So you were not saying that, but it was said that posterior should not be believed in because it always depends on chosen prior. I think that also using frequentist methods, so in my opinion, means actually choosing a prior in the way that is maybe not as obvious as in Bayesian approaches, and therefore I think also using frequentist methods should be taken with a grain of salt, because there's also many assumptions going on there, for example regarding repeatability ad infinitum of the experiment. But yeah, thanks for your talk.
Well, I actually have a slide later in this set that says basically what you just said, that frequentist results, it's basically the box point from like 1980, that frequentist models are priors themselves. They are priors about the dose response shape and so forth. In fact, they're very sharp priors. And so I discussed that later from a general viewpoint. So yes, we agree. And I just didn't have time to go into all those kinds of details.
Okay, cool. Yeah, thank you so much.
Now we've got a question from Ian White, followed by one Jason Oak. So if either of you want to come pop up, otherwise I will start reading Ian's.
Mine wasn't a question. It was just an observation that I found the prior for the ivermectin, but it was buried on page 163 of the supplementary materials.
Mm-hmm. And send it to me so I can compare it to what I back calculated, because I don't really know for sure what they had. I couldn't find it in the main text. To me, that's the whole issue. It should be stated right there in the main text, just like you state we used a Cox model. Well, we used a prior that did this, that has 95% limits from there to there, for example. So I know what the heck you're dumping in with the data to get these results.
Okay, Jason, would you like to speak, or shall I?
Yeah, I can. Yeah, I can.
It's better, I
it's
think.
Really just a comment. It's really just a comment as well. But thanks for the talk. I really enjoyed that. I think at the beginning, Sander, you'd said something about teaching statistics that really struck me. I think you were saying we should focus more on teaching kind of cognitive biases rather than maximum likelihood. Is that what you said, or did I misinterpret?
Yes, you got that absolutely right.
That's very interesting. I don't know if you've tried doing that.
Well, I have in workshop settings. I have a bit in the classroom. Now, I retired from regular classroom teaching 13 and a half years ago. Well, the last time I did that was maybe 12 and a half years ago. But I was starting to do some of it. I did that for quite a few years, to some extent, to a large extent, displace that. And I used readings from people like, of course, Kahneman and so forth. But I can't say that it was a completed experiment. And besides, it would only be an instructor sample size of 1. So I don't know what you would get out of it. This is just something that I think what I see of what's going on is, like, at the very least, if we claim it's because they're misusing our methods, we are responsible for seeing how they're misusing their methods and coming in with methods to try and prevent abuse of the methods.
Great, thank you.
Well, thank you. Now we've got a question from Hin Wan Chen. Sorry, I probably pronounced that wrong. I'll read it out, shall I? Unless you quickly pop up. Great talk. I'm curious why P is greater than 0.05 is routinely taken to mean no association or evidence of no effect. If we try to interpret P is greater than 0.05 more carefully, do we risk overinterpreting the finding?
Can you repeat that last part again?
If we try to interpret P is greater than 0.05 more carefully, do we risk overinterpreting the finding?
Well, actually, the problem is that people overinterpret P greater than 0.05. Well, they misinterpret P values, period, whether they're above or below 0.05, but they certainly misinterpret them over 0.05 much more than what I see in the literature, much more than less than 0.05, in that they interpret them as this supports the null or there is no association. I showed you examples of that. This is the problem is the overinterpretation of P greater than 0.05. The whole idea is to try and get around that by interpreting it more carefully, by pointing out when and how this is usually a sign that the results are ambiguous. But then, of course, I can see why people have been saying this for over a century. I can point to articles going back before my grandmother was born that are talking about this. And why does it never catch on? Because then what happens? Your study is now ambiguous instead of having revealed no association. And how much harder will it be to publish? Well, way harder to publish in any place, prominent especially. So this is the general problem of publication bias in a sense. But this time you can get publication bias by actually encouraging people to overinterpret nulls. Okay, that's not something I see recognized in the publication bias literature I know of.
Okay, we've only got 3 minutes left, so I'll just read them quickly out. The next one is really a comment by Mark Temple. I think Simon D's point is exactly what patients report every day, that their treatment did not have the effect promised, sometimes better, other worse. Comment. Don't know if you want to comment on that.
I'm not sure what the question. What's
it's just a comment. It's just a comment.
It's a comment, and the comment is, I'm sorry, you'll have to read it again.
I think Simon Day's point is exactly what patients report every day, that their treatment did not have the effect promised, sometimes better, other worse.
Yes.
Okay, there's another one. Thank you, Professor Greenland, for the talk. As an early, this is Michael Poon. As an early career researcher, it seems that there's often a disconnect between study design and statistical approach in addition to misinterpretation. What is your advice for ECRs when discussing these aspects?
Yes, okay, that's a long, I don't know if I can answer that succinctly, especially in the time given.
We've only got 1 minute, so maybe we should wrap it up. Janina, do we need to finish now? Are you still there?
Yes, I'm still here. So yeah, it's up to you. If you wanted to read one more question, just popped in, or you want to wrap it up.
Let me just have a look. This one. Actually, I like this one, so I'm going to read it. Paul Marchant, surely we should be demanding open data so claim results can be checked and alternatives suggested. So I don't know what your thoughts on that are. I'm sure they're.
Well,
yes.
I'm very much a radical open data camp and open publication. I mean, I think it's outrageous that, for one thing, the public important decisions affecting the entire public are based on hidden data. That public pays for collection of data and then can't access it. That the public pays for research that's published and then can't access it without paying $50 or whatever to a publisher. This is all just madness to me. The whole thing is like, how did this happen in a society that's supposed to be thinking in any kind of at least liberal terms, if I can use a politically charged term, that all the data should be, the data sets that were used to produce the results in these studies, they should all be carefully aligned and formatted. That should be a condition of, I think in my ideal world, it would be a condition of publication, that A, the data sets are available and documented, and B, the articles, the writings, everything is also available. Whatever costs involved in doing that should be covered by the grants. But we all know about the problem with the publication houses and what that's produced. Luckily, the internet is providing a way around that, at least with archive and so forth. But anyway, that's my views. They may be radical, but I don't think they're uncommon.
I think probably most people agree with you here. I certainly do. I think that's a really great way to end, because yes, and a really good question to end with. What we can do about it, I don't know, but yeah, well, maybe you have some ideas of how we can make this happen.
Well, I have my ideas, but of course, it's not like any of the ideas, mine or others, have been tested in randomized trials. How would we even do that? This was the biggest problem that I see in methodology and in this, what I'm talking about here, which could be called a meta-methodology. And that is that the less data that we can have, and we could even obtain, the more vociferous our opinions will be, because there's no danger of refutation by an experiment. There is an interesting, this phenomenon is commented on by some physicists in particle physics, for example. There are people who vociferously promote this or that interpretation of quantum mechanics, they say, like many worlds, or some rabid believers in that. And it's kind of remarkable to see almost the religious devotion that they attach to these ideas. And there are others, the more skeptical colleagues, who will say, yes, that's all fine and well, because there's absolutely no danger that we'll be coming up with any experiment that could tell that apart from any other of 40 other proposals floating around. So that's a thought to for all this, but I think we still have to press forward. And I gave one, and I have several other, many simple solutions that you can implement immediately to improve the situation. I've seen it improve when I've worked with people. It helps to compute multiple p-values for alternatives, to stop calling these things confidence intervals and significance tests, all these value-laden words, like we're going to find the significance of something, we're going to have confidence in this. That's all absurd. Under these conditions, I call them, so I say, just call them compatibility intervals. They'll show you what's compatible under the model, what's compatible with your data. Call them compatibility, p-values compatibility measures, as Carl Pearson did back when he used the value of P. He talked about compatibility. Fisher did in his examples. You can see them. Then Cox called it consistency with the data. You can give a much more modest, ordinary English description of everything that we're doing that won't deceive people into thinking that it's providing them with what is significant or what they can be confident about, because it's not. It's not doing that. And I think the use of these words, especially confidence, as was said by Bowley when Neyman gave this big presentation, I think in 1934, to the Royal Statistical Society, introducing formally confidence intervals. Bowley said, this looks like a confidence trick. And it was. It's just a sales pitch. It's a sales thing, like save now and all this sort of stuff. It's on that level. There's no basis in most of these applications for having any kind of confidence in what's produced. And then they'll say, oh, but confidence refers to the method. Do you think the ordinary user or researcher will understand that distinction? No. And you can see with the way they use it and write about it, that they don't have a clue. So stop using deceptive language. And that's what a lot of the slides eventually end up here talking about, is ways we could just do simple things to help. Maybe it's using a broom to sweep back the sea, but hopefully will help clear the path a bit for better interpretations.
Oh, thank you very much, Sander. It was a really great talk.